What you're going to do now is take what you've just learnt about sec, cosec, and cot and use what you did in Pure 1 when you had to prove and use trig identities. You're kind of going to marry the two now. So, that being said, part A, can you give it a go, please? So, let's consider the left-hand side first. And let's split the numerator and the denominator. We'll work with them separately. So cot theta and cosec theta. We want at the end to have cos. So we want to convert cot and cosec into sine and cos if we can. How do we convert cot into sine and cos form? It's cos theta over sine theta. And then cosec is 1 over sine. This gives us cos theta over sine squared. And then we can't really go further from that. So this is the numerator. Now let's work with the denominator. Sec squared plus cosec squared. Again, we want sine and cos. So 1 over cos squared plus 1 over sine squared. If we try and put that into one large fraction, what would it look like? It would be sine squared plus cos squared all over sine squared cos squared. Okay, because sine squared cos squared is the lowest common multiple, you have to times the first fraction by sine squared, the second fraction by cos squared. Your identity from last year, sine squared plus cos squared equals 1. So 1 over sine squared cos squared. And to go from here to here, you're using sine squared plus cos squared is 1. Okay, you can't go any further from here. So now you're going to put the two together. You're going to put cot theta cosec theta, and you're going to write that as cos theta over sine squared, and that's divided by your denominator, 1 over sine squared cos squared. Okay? What do you do from here? From here, you can flip the fraction on the right hand side and make it a times. Since this is over 1, I can ignore the over 1 because it's just going to be the same. And now, simplify. So sine squared cos cubed over sine squared. The sine squares cancel out. You're left with just cos cubed. And that was the question. Prove that the left equals cos cubed. And we just did. Perfect. Part B. Hence explain why the equation blah 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 equals 8 has no solutions. The blah 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 equals 8 is the same as cos cubed equals 8. If we want just cos, we have to do the cube root of 8, which is 2. And now there's no solution for the inverse cos of 2. There you go. Because cos has to be between 1 and -1. Okay? Right. That was quite long. I can see why it would be confusing. So feel free to watch that back as many times as you like. Make sure you understand why I've done each step. That's really key. Okay, so can you try that question for me, please? Okay, part A. I find it's always easiest to go from left-hand side to right-hand side. So let's start with the left-hand side. Let's convert cosec and cot into the sines and causes. So cosec is 1 over sine minus cos over sine divided by 1 minus cos. Okay, now let's group the numerator. If we group the numerator, we get this. Okay, and now from this point, you're doing 1 minus cos x over sine x divided by 1 minus cos x. These two cancel each other out. And you're left with 1 over sine, which is cosec. Did that make sense? You're doing 1 minus cos as a numerator divided by 1 minus cos as a denominator. The two cancel each other out. You're left with 1 over sine, and then equals cosec. Part B. Hence solve in the interval. Notice that it's in radians. Your fraction equals 2. Well, we know our fraction simplifies to cosec x. So we're going to make that equal to 2, which means 1 over sine is equal to 2. So 1 equals 2 sine. Sine equals a half. Now, when we do the inverse of that, and we're doing it in radians, so the inverse of sine of a half gives pi over 6, which fits our interval. We do the cast diagram. Like this. Pi over 6 is going to go somewhere here. And it's sine, so it's going to reflect somewhere there. So this is solution 1. That's solution 2. To get solution 2, we're doing pi minus pi over 6, which is 5 pi over 6. That's the second solution. And there you go. That's how you use sec, cosec, and cot in trig identities.